Hey, welcome back. Today we're going to be talking about how do fiber optics work, including what is total internal reflection and how to think about that, what a critical angle is, and this is for physics students primarily or physics type classes, maybe even AP physics, so let's go ahead and get to it. I have talked in the past about refraction. Hopefully you've been exposed to that. If you haven't and you want more information about that, before we get started, here's a background screencast to help you understand what I'm going to be talking about today. I'll put that in the upper right about now. Alright, let's get to it. So first of all, we know that light will bend as it goes from one medium to another. So this light source that you have down here is going to send off a light ray, and as that ray goes from one medium to the next, from a more dense medium, this is water right here, to air up here, it's going to get bent as it goes from one medium to the next. We say that is refraction, and in this case it's being bent away from the normal. This is the normal line that is perpendicular to the surface involved. Alright, well that's the case. Well, what if our incoming angle is measured from the normal right here, like we have this normal over here? What if it was a greater angle? Well, let's think about what would happen. So if you think about it, what would happen to this angle that happens to be on the back side of this? Would it be a greater angle like this or a lesser angle like this? What do you think? Well, it's going to be an even greater angle, right? Well, can you anticipate what's going to happen next? At some point, you're going to send a ray off at some angle, and what do you think is going to happen at that point? Something interesting. Well, yeah, it's going to come off at some critical angle as measured to the normal, the perpendicular line to the surface. It's going to come off and it will refract right along the surface as you go from one medium to the next. So right along that surface, we'll have this light travel right along the surface right here. So that critical angle is actually really important. And any angle greater than this value is going to be refracted, but it looks like it's just reflected back. So let me show you an example of what I'm talking about. This right here is called total internal reflection. So total internal reflection is the idea that light just gets bounced as it goes from one medium to the next. Instead of getting refracted down the line, it's a big enough internal angle here. This initial angle right here is measured to the normal is going to be large enough that that light ray just continuously bounces on the inside of this substance. And you might think, okay, that's neat and all, but what does that even do? Like, alright, I don't see where that's going to be helpful in my life. And my question is, are better internet speeds helpful in your life? Because this idea of fiber optics is based on what I'm talking about here, and it's how we're able to get better internet speeds, better data transfer rates. You might have computer parts in the future being built using optical components as well. And one of the really cool things about using light instead of electrons and currents and potential difference through wires is that light travels insanely fast. It's the fastest thing in the universe, and there is very little energy loss if you compare talking about light, sending energy with light pulses, as compared to electrical current. Alright, so you could have a scenario where you have an object under the surface of water as you go from water to air, and it would get refracted or bent back in such a way that it looks like it's been reflected back. You have this total internal reflection. Let me show you an example of what it is exactly that I'm talking about. So let's take a look at this swimmer right here. You can see like the back of the swimmer because really the light rays are going up to the surface of the water and they're getting reflected back to us. And it's not that the surface of the water has a mirror on it, it's just acting like a mirror because we're dealing with this total internal reflection. Pretty amazing stuff. Now, we can use this, and the way that we're going to most commonly use this in our everyday life is benefiting from the technology of fiber optics. So if we imagine this is again a greater N value in here, and this is a lesser N value, so this would be like a glass or silicon based fiber most commonly, and then this outer core would be made of like a clearish plastic or something along those lines. And if you did something like this, you can have total internal reflection, which means the light ray is going to bounce as if it's following the law of reflection all the way through. If you're not sure what the law of reflection is and you want more information about it, I'll put a link to that lesson I did on that in the upper right about now. but this is going to follow as if it was just following the law of reflection and just keep bouncing. Nearly all of that energy is going to stay on the inside of that inner core, you could say. It's not going to spread out to the outer core or get dissipated very much at all. There is some energy loss, and I do need to talk about that. But one thing you should know is that you can have as many as several hundred total internal reflections per centimeter. So even in a centimeter, you can have multiple hundred reflections. And if any of those have some sort of small defect, then some of that light can escape, some of that light can leak out, so to speak. And so that's why there is some energy loss there, you could say. Now, given that there are several hundred internal reflections per centimeter, it's amazing that you can lose only 25% of the energy per kilometer. And this is an optical fiber here, and so it's only losing a quarter of the energy for every kilometer, even given the fact that it would have multiple hundred total internal reflections. So as long as you have good materials, for the most part, you're going to not lose much energy. However, as an engineer, you would have to build some thought into how to amplify that light as it comes through and reinforce the information that's encoded. Let me back up for a second and mention that part of the beauty of beaming light through fibers is that you can transmit massive amounts of information with those light pulses that you send. So every pulse can be like a 1 or a 0 in a binary sense. And you can do this with all different colors of the rainbow, so to speak. And all of these can transmit different data sets that then can be combined later for a massive amount of data transfer. So pretty amazing stuff. Now, how do we calculate the critical angle here? I'm going to start with Snell's law like we have right here. So one thing I should mention, we did talk about this as a critical angle right here. So I'm going to just change the subscript to a C for critical angle. Remember, in physics, these subscripts are there to help us, not the other way around. They're just labels, so we can change those labels to be whatever we want to make them easy. And the next thing I want to point out about that equation is notice that the second theta right here is going to be 90 degrees. And this happens to be sine. Sine of 90 degrees, does that ring a bell? What is the sine of 90 degrees? Well, the sine of 90 degrees is going to be 1. So then we would have n2 times 1, which is just n2. So we can kind of ignore this in this case for this equation. And just a reminder, I'm going to put a question mark by this, meaning like that is what we are looking for. So I'm going to show this to you in two different ways and use whichever way is more preferable for you. This goes away right here, and if you prefer 1 and 2 subscripts, then what I would suggest is we go with this equation right here for the sine of our critical angle is equal to n2 over n1, and the exception is for n1 is greater than n2. I'll explain what that means later. And then if we isolate for our unknown, remember this is our unknown right here, we really don't want the sine of the critical angle, we want the critical angle itself. So we take the inverse sine of both sides. If you do that, you end up with this equation here. Or you could write this another way. If instead you don't prefer the 1 and 2 subscripts, if you prefer the I and R subscripts, kind of like your incident ray and your refracted ray, then you could write something like this. And if we do the isolation, then you would end up with this as your final equation for the critical angle. One last thing I want to talk about, and that is why does the critical angle equation assume n1 is greater than n2? So let's think about this really quickly. We can say, in this case, this is the scenario that we described before, this would work, or if this was like, say, glass and air, or glass and like some polymer out here that was kind of clear-ish, that would work right here. If you had something like this, let's think about what would happen. What direction, in this case, if we're going from an n1 that would be less and an n2 that would be greater, then what direction would the light get bent in this case? Hint, your answer should be either it gets bent towards the normal or that refracted ray would be bent away from the normal. So what would you expect? Well, in this case, the light ray would get bent towards the normal. And if you think about it, that's not going to be total internal reflection because this is our initial medium that we're dealing with up here. And light rays are not just bouncing through the atmosphere and just traveling in the atmosphere. It's actually leaking out of one medium into the next. It's actually less inclined to stay in that one medium that it started with. Like we have up here, it's the opposite down here. So we always have to assume that we're dealing with an n1 that is greater than n2, or else it won't work. We won't get total internal reflection. In any case, hopefully this has been helpful. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.